Welcome, everyone. Thank you for this opportunity to talk about some of the work I've been involved with, some at the university and some out at the private sector. Um, my name is Timm. I'm a founder of GT Urological, and I'm professor of urology at the University of Minnesota. Today, I'm going to talk about, I'll give it a little bit of talk about my background, talk about how we do our opportunity identification, talk about intellectual property, how we structure corporations to commercialize technology, and different funding sources that are available to make things happen. I'm going to do this in the form of a variety of case studies, which different opportunities I've had to bring technology to market by founding of corporations. My background, I started off as a student at the University of Minnesota in electrical engineering, ultimately joined the faculty in the medical school, in neurology. I watched my classmates in my graduate school starting companies. So as I got involved in research, I helped start a company, Mentor Corporation, and later American Medical Systems, and Dacomid Corporation was my third company that I was co-founder, or actually I was a founder of that one. Founded Timm Medical Technologies in '97 and GTR Logical in 2002. And I rejoined the medical school faculty in 2003. I call it the bookends of my career. I started off in the medical school faculty, spent about 25 years out in the private sector, and came back on the faculty in 2003. How do we determine what is a real opportunity? We typically get involved in research and really don't spend a lot of time thinking about market, but obviously that's a pivotal thing that we need to think about. Clearly, in order to do something commercially, you want to have some proprietary technology so that you can protect yourself when you get out in the marketplace. Clearly, when you evaluate an opportunity, we look at return on investment. If you're trying to attract funding and different people to get involved in your company, they're going to want to know how do they get their money back and hopefully a little bit of a profit. Clearly, any product that you develop has to be manufacturable. Something I learned early on, even though I spent time making a lot of things before I really focused on the manufacturability and came to realize how important that is to get involved with the manufacturability early on in a product development. And the other thing that you need to look at is you need to have a product champion. And whether it's you as the inventor or a physician or another colleague that you're working with, somebody needs to have some kind of a passion for the technology. In urology, there's an overlap between the business aspect, the medical aspect, and the technology aspect. And where they coalesce and where they come together in the middle, that's where you have the real opportunities, when they all complement each other and allow you to expand and grow. The different areas of urology that a person can get involved with, the areas I got involved with were erectile dysfunction and incontinence, but there are a lot of other opportunities of disease states that lend themselves to technological solutions. My focus initially was in urinary control disorders. I was originally recruited to adapt pacemaker technology to urinary bladder control by a neurologist who was interested in spinal cord injury. So in urinary control, these patients that have lost the upper control of their bladder, they need to have some artificial devices to help manage their leakage problem and voiding problem. So what is the problem? You start with, and you start by looking at the market size, who's affected and why, and then you look at what can be done. What is needed in the way of evaluation of patients or diagnosis to select appropriate therapy for them, and then what is the appropriate therapy? Looking at the anatomical, there's some anatomical differences, obviously, between male and female, but it's easy to point out that the area of the urethra for the female, urinary bladder urethra, is only about 4 to 5 centimeters long, whereas in the case of a male, it's more like 22 to 25 centimeters long. So it's a kind of a little different anatomical apparatus. Additionally, the male has the prostate gland that is located right at the base of the bladder, which is not so prevalent in the female. How does normal voiding occur? And so here's an example where water is infused, or saline really is infused into the bladder, and the top curve. Line 1 shows shows the voiding. The second one shows the sphincter electromyographic activity, and the third one shows the bladder myographic activity as the bladder is filled. And ultimately, here's what it looks like, and here's what the cystometric would look like in a healthy volunteer. You have some pattern of activity initially, and the two little spikes are when they first feel urgency, and ultimately it leads to voiding. Urinary incontinence is a big problem in this country. When I did this slide, I estimated there were 13 million U.S. adults that were afflicted. I've come to find out that's probably pretty conservative, but there's quite a few more worldwide, maybe 200 million. It's one of the leading causes for nursing home admission because sufferers become prisoners in their own homes. They don't want to go out socially because they have problems controlling their bladder. So some of the market dynamics in the diagnostic area, the procedures are increasing. There's getting to be better and better reimbursement for testing. There's a variety of self-care or rehabilitation products that are being used, and they're growing quite rapidly as well. Things, self-care, bulking agents is another area and I'll talk about these a little bit later. There's a variety of different plugs or things that are put into the urethra to prevent leakage, and the existing artificial urinary sphincter, which I'll talk about in a bit, is currently probably implanting 6,000 or 7,000 per year. Additionally, there are slings and suspensions procedures that are increasing rapidly as well. When you look at the overall size of the market, you can see that $26 billion is being spent annually to manage the problem, but products, $2.7 billion are management products, and treatment products are only about $230 million. So you can see the bulk of it is spent on managing the problem. The difference between the 26 and the $3 billion is what's being spent for healthcare professionals and nursing homes and expenses associated with people maintaining or controlling their urinary tract. So trends and opportunities, you can see there's an increasingly aging population. The baby boomers are more interested in self-advocacy toward treatment products, and but there's always an opportunity for innovation, and there's also an opportunity for consolidation, particularly in the female market. Here's some of the products that are currently out there, and most of those you're probably familiar with. Go to any drugstore and you'll see the Depends and Kimberly-Clark and the different companies that manufacture them. There are condom catheters for men that they connect to a collection device. There's penile clamping devices, one of which I helped develop, but it's about a $2.7 billion market. So there's a lot of, it's a large market, and there's still opportunities for improving it. So when you split it down into diagnostic versus management, you can see most of the money is being spent for management products. And those are things like absorbency pads and things like that. Some of the therapeutic methods that are being applied are bladder stimulation for people that can't evacuate their bladder. Urethral occlusion is a device that basically squeezes the urethra gently to keep urine from leaking. And bladder volume sensing is a way to tell when to empty the bladder. So I'm going to talk about 5 different case studies here. The first will be the technology that we developed originally at the university went to a private company. The public domain information that went to a private company. The R&D company went to a manufacturing company, ultimately to a distribution company. So it kind of was a merger or a combination of companies that were put together. And then the private company that purchased a division of a public company, and then a private company with SBIR funding. So the first study, case study, is I had developed a device for bladder stimulation, which was comprised of some unique electrodes and some technology for applying the signals in an appropriate way. We got a patent from the U.S. Patent Office and started a company, Mentor Corporation. And this was, as I mentioned earlier, some of my classmates were starting public companies. So one of my classmates told me, hey, Gerry, we can take this downtown and you write a little story and you can raise $300,000 in a local over-the-counter market placement. I said, oh, I just gotten my first NIH grant at the university. It was $35,000 a year for 2 years. And I said, and I can raise 300,000 with, anyway, so that's what we did. We started the company and built it up. It ultimately achieved quite a significant amount of sales, about over 400 million at the time in 2004, which is the last time I had information on it. Made a nice profit and had a good market cap, and ultimately sold the urology division of Mentor to Coloplast in 2006. And to the best of my knowledge, Coloplast still runs that urology division. We sold the cosmetic division of Mentor it was sold to J&J in 2008, and the rest of the remainder of the urology division was then also sold to Coloplast in 2010. The second one is some other technology that I developed. This was still while I was still at the university, although at that time we didn't really have a very aggressive, shall we call it, patent office at the time. So we were just publishing like crazy. We published everything we developed, and probably made a mistake. We probably should have been a little more diligent in filing patents, but we didn't. But anyway, we developed a variety of fluid energy transfer devices. The first one was a device for urethral occlusion, which had an inflatable cuff, which pressure was carefully maintained, and you can see on the pictures where it was placed. It was placed the pump was placed in the scrotum for the female, in the scrotum for the male, and in the major labia for the female, and with the device with the cuff itself placed at the bladder neck for the woman, and in the bulbous urethra for males. So we started another company, American Medical Systems, and ultimately engineers devised the artificial sphincter, but also using a different apparatus, we also developed an inflatable penile implant using that same hydraulic fluid energy transfer devices. So here's some of the early publications. You can see they date way back to 1971. We developed that first implantable incontinence device, and then developed an external device for men to manage urinary incontinence, which was basically a penile clamping device, and then developed the inflatable fluid transfer system for treatment of impotence, came in 1972, and so on and so forth. And so ultimately, these were brought to the market. I think we did the first patient implants in 1972. Here's an example of the occlusive cuff as it was earlier configured. It had a series of 4 or 5 sutures in the back that were then tied and formed into an annular ring. And the process of inflating that and maintaining the pressure was enough to stop urine leakage, but not so much as to cause tissue ischemia. And so that was the way it was placed in the case of the male, placed in the bulbous urethra. And we did some tests on occlusion efficiency to make sure we had the right dimensions and geometry, because everybody's anatomy might vary a little bit. And so we did a series of tests on occlusion efficiency. And ultimately, we ended up, the original device had 2 pumps and the cuff and a reservoir. So you can see the inflate bulb was the device that caused the pressure to go up into the cuff. And the valve V4, if you can read that in the slide, is the one that was a check valve that actually set the maximum pressure that could be achieved in the cuff. The valve V3 was just basically a it was a ball-free valve that prevented backflow when you hit the deflate bulb. So the way to operate this is you hit the inflate bulb. It might take you 2, 3, 4 pumps before you get the cuff fully inflated, but you can't overinflate it because valve V4 limits the maximum pressure. To empty your bladder, what you do is you take the deflate bulb and repeatedly compress it, and that pumps fluid from the cuff and puts it back into the reservoir and ultimately deflates the cuff. And so you can see the construction of the check valve up in the upper right-hand part of that slide. Here is the original AUS. Like I said, it was 2 pumps, and the bulbs were placed in the scrotum in the male and then placed in the major labia in the female. It was totally implanted, no tubes or wires coming through the skin. So once you got it in place, and assuming you did it with a good surgical procedure, clean procedure, and avoided any kind of infection, the thing would last indefinitely. The new device, or the more current one, is really only has one pump bulb, and the little balloon-looking feature you see up there in the top is actually a pressure regulating balloon. It's designed so that it holds a certain maximum pressure, and the maximum pressure could be set anywhere from 60 to 80 centimeters of water, which is enough to inflate the cuff and prevent urinary leakage, but not so much as to produce tissue ischemia. You want to stay below diastolic blood pressure. In this case, the device is deflated by pumping on the squeezing on the pump bulb, and you squeeze and it pulls fluid out of the cuff and pumps it into the balloon reservoir, and then the balloon, there's a little delay fill resistor in the top of that bulb so that the cuff automatically refills in about 3 to 5 minutes. So it gives the subject plenty of time to avoid their bladder, but and then automatically repressurizes. And here you can see the cuff placement in the case of bladder neck, which is where it was used mostly for females, and in the bulbous urethra for males. Then in 1966, a new age came upon us. Masters and Johnson published this book on human sexual response, and we're trying to figure out how to introduce the penile prosthesis to the market. And so we went to visit Masters and Johnson, and they said, well, you do it through the professional group. You talk only to urologists. You don't advertise in the newspapers. You just go through the medical community, and so that's what we did. We set up a series of workshops, so we trained doctors on how to do the surgery. We typically have 2 implants, one sphincter and one penile prosthesis, and that was how we trained the next generation of surgeons to implement this technology. So this is the erectile dysfunction overview. There were probably 85 million impedance device, $1 million, that's dollars, not devices, in 1998, with 130 million impedance device market in 2001. But there's a lot of impotent people worldwide. This, I think, is pretty conservative. 50 million is probably on the low side, with 25 to 30 million American men. But market awareness and patient admissions are increasing as people become more comfortable with it. Significant diagnostic opportunity in urology and with primary care physicians to expand that market and make people comfortable with it. Here's some devices that are available. The device we developed was an inflatable device, but there's extensive R&D is done, but it's mostly pharmacologic. As you know, later on, Viagra and Cialis and these other pharmacologic agents became available, but they only work in people that are pretty much intact. If they have some underlying anatomic problem, they're going to probably need a prosthesis or some kind of reconstructive surgery. There's an increasing emphasis on doing proper diagnosis, and also there's another aspect of erectile dysfunction called premature ejaculation, which is also getting a fair amount of attention. There's continued use of devices in 5 to 10% of the cases. It's not a panacea for everybody, but it makes a big difference in people's lives that do get it. And there's now new R&D going on in female sexual disorders, which kind of hard to figure what a device might be for that. But anyway, there's a lot of studying being done currently to help deal with that situation. This is what the AMS inflatable, well, we call it the AMS inflatable. It's now owned by Boston Scientific. They acquired the company a few years ago. But there's basically 2 cylinders that are inserted into the corporate bodies of the penis, and there's a pump, again, placed in the scrotum and the reservoir in the abdomen. And the process of inflating the device, there's a bulb portion of the pump that you can see in the scrotum, and then there's a square portion. Well, the square portion is a release valve. So by squeezing crosswise, that allows the prosthesis to deflate and the penis to detumesce. American Medical Systems in 2009 had about $500 million, I should say, in sales, and was fairly profitable. Had a good market capitalization, and its growth continues in incontinence. The company was purchased by Pfizer in 1985, and later was taken public, and so on and so forth. So it's kind of moved around a little bit. And Today, the company no longer exists. The name American Medical Systems, as I said, it was acquired by Boston Scientific. The product still exists, but the name is gone. So the third case study I was going to talk about is while I was at AMS, actually, I developed another version of a prosthesis. I call it a malleable penile prosthesis, and it was basically a device that was like a cigar-shaped device or a pair of them, and the process of bending them, they would hold that position. So we call it a malleable penile prosthesis or a positionable device. But it would give the man really a permanent looking erection, but he could conceal it. You know, like if he went in the shower or whatnot, he could position it in a down position that made it look more natural. So we used distribution companies to use R&D to develop proprietary technique. We were a distribution company. We used R&D to develop proprietary technology. The NPTR is an example of that. An NPTR is nocturnal penile tumescence and rigidity. And this is a test that's a diagnostic test that's given to men that have the complaint of erectile difficulties, and it's done during sleep. And they monitor penile activity during sleep. And in this case, we monitor two areas, one at the base of the penis and one at the tip. And so we measure tumescence and we measure rigidity. So the lines, just the lines, that's the tumescence, and the solid lines, that's the rigidity. So when the penis would reach a certain size, it would become rigid and become unbuckleable. So this device was a way to determine if that was the case. And the physician who developed this was a psychiatrist actually in Houston at the VA down there, and he originally developed just an NPT, and he did about 4,000 studies in males, and he found all males from about 3 to 83, I think is what he had in his study, have from 3 to 6 erectile episodes per night of restful sleep. And the absence of that is indicative of some kind of an anatomical abnormality. If it's poor vascular supply, it could be a variety of things. It could be a neural injury or other pelvic trauma. Anyway, there's a variety of reasons for it. And this would help with the differential diagnosis of that problem. Here's more of one for a younger man, 35-year-olds, but you can see they don't look that different. And so but it's turned out to be a very useful test for use in the differential diagnosis, or sometimes just for education. They'd have the men do this test, the sleep test, and then they talk to them about it and just explain what was going on and what it meant for them. Here's an example of the device. The RigiScan system is the one that measures tumescence and rigidity. The snap gauge was intended to be kind of a screening test, kind of like a home pregnancy kit, but it was supposed to be indicative of if a man was in trouble. So it had 3 plastic elements that broke at different force constants. So if he broke the first one, it was probably, could still be considered fairly normal. But if he broke 2, or certainly if he broke all 3, that meant he had a pretty good nocturnal erection, a pretty rigid erection. And so, but typically it was only a screening test to tell them if they really wanted to keep going forward, because if they broke all 3 elements, there's not much point in going any further with diagnostic workup. But that was at least the premise behind it. It was applied in the mid-shaft portion of the penis, and here you can see the elements. There's 2 of them are broken. There's a blue one, a red one, and then a clear one is the last one, and just kind of indicative of what the status is of that particular individual. In the sense of, and for urinary control disorders, there's a whole series of different tests that are done. There's flow meters, there's cystometers, there's a variety of different instruments that are used to measure bladder strength and activity combined with sphincter electromyographic activity. So there's a variety of instruments that have been developed over the years. So I started another company, Decomed Corporation, and where we made the RigiScan. We made a variety of urodynamic equipment, and we achieved almost 10 million in sales in '95, marginally profitable, but then sold it to a company out in California called UroHealth or Imogen, and they were looking for technology to add to their product line. So So then the next one, I continued to work on a device, another sphincter device, a urethral occlusive device, and I obtained a license from EuroHealth so that I could continue working on this product, um, and set up a distribution for this product, and ended up acquiring. First, I acquired Brown Medical, which uh, was a urodynamic company, and then I came back and purchased Imogen, which had the ED products, had this penile prosthesis. So here's some various devices that are available for urinary incontinence treatment. There are the urethral slings, which I'm sure many of you have heard about, manufactured by a variety of different companies. The artificial sphincter, which was developed originally by American Medical Systems, now owned by Boston Scientific. And then there's a variety of injectable bulking agents, which are really a way to cause the urethra to coapt and to increase urethral resistance. But it's still a very large market. Generally has poor long-term durability, no current single option for both men and women, even though that was what we originally had in mind when we developed the artificial sphincter, was that it was intended to be used, well, we thought primarily in women. We hadn't really even thought about it so much for men, but in urology, it's kind of hard to ignore men that have prostate operations and sometimes end up having some minor leakage problems, and it turned out to be a real beneficial device for mostly for men at this point. Some other erectile dysfunction therapeutic devices, vacuum devices, they were originally developed by a tire recap company down in Augusta, Georgia, and he had a problem himself and knew about negative pressures and knew that if he could apply negative pressure to his penis, he could get an erection. And then they had a little rubber band they slipped off the end of the tube so that they could maintain that rigidity for a period of time. And then we also developed another more, it was not a malleable prosthesis, it was a positionable device because it was consisted of a series of nested segments, and with a cable that went down the middle that was held in tension by a spring. And so, but it was probably the most positionable of any of the malleable devices. And here's what I told you before about how the vacuum device, you achieve an erection, you slip that little rubber band over the base of the penis, and it'll help you maintain erection. Here's some different, so we were developing a new artificial sphincter, and so I was doing a comparison between the AMS 800 and the device we were working on, which was basically a cable tensioning device, a mechanical device rather than hydraulic. So this is kind of what it looked like. It had a loop like we had before, except in this case it was EPTFE and it had a cable running down the middle of it. And if you pressed on the plunger at the end of the apparatus, it would cause the loop to expand and thereby decompress the urethra. And then it had a little button on the side of it that you could compress, and that would re-engage the device. The cable is used to open and to allow voiding, and activation button on the control mechanism releases the cable to allow closure of the cuff. Timm Medical, the company that I started to put this, that I used to put these technology together, it had about 16 million in annual sales, it was break even, and then we sold it to Endocare in 2002. So Viagra hit the market in 1997, I believe it was, and this was a device that was being developed in the UK ostensibly for an antihypertensive, and they decided to purify it and reintroduce it. It started in '89. They're doing the study, and many of the men that were part of this antihypertension study didn't want to leave the protocol because they were having these desirable side effects. Anyway, that's inspired Pfizer to continue with the development of Viagra. And I still think to this day they probably would not have done that had they not purchased American Medical Systems in 1985 and seen that there was a legitimate human need for this technology, and that there was a real opportunity there, which obviously they've been very successful with introducing this to the market. So, so we're kind of changing direction. That's why I said it was originally supposed to treat angina and antihypertension, but it went on to treating erectile dysfunction. So here's an example of something that goes from the lab bench to clinical testing pretty rapidly. And then it got launched, and like I said, I think it was about 1997. And we actually played a role in that as well because of the rigidity device. Pfizer engaged us. I think they had us make 125 of these devices that they gave to each of the clinicians that were testing the Viagra. And so this became a secondary benefit for this device. In addition to being useful for diagnostic purposes clinically, it could also be used in a research lab for product development testing. And as you know, the thing really changed when Bob Dole came on public television speaking for Pfizer about openly about erectile dysfunction. This is a legitimate need for men, and not nothing to be make fun about. And you can see the medical literature shows the increased interest in ED, and the publications have exploded in the last couple decades. Here's a letter that was sent to one of the doctors, and he gave me a copy of it. And anyway, I thought it was kind of humorous. Writing to tell you my problem. It seems I've been married to a sex maniac for the past 22 years. He makes love to me regardless of what I'm doing, ironing, washing dishes, sweeping, etc. I'd like to know if this is something, and then the writing kind of fades away. Anyway, I thought this was kind of humorous. But anyway, it's a legitimate need, and there's been a lot of stories told over the years about ED and Viagra and so on and so forth. But as you can see, as the Viagra came to the market, you can see what happened to the vacuum erection device market. It kind of fell off the roof, and it's gradually coming back, but it'll probably never come back to where it was back in 1997, 98. Case study number 5 was this is an example of a private company that I used SBIR funding to launch. So I started in 2002, acquired the license for the patents from Timm Medical Technologies, which is my former company, applied for SBIR funding, and we got quite a ways down the road with it. Actually started doing and got to the point of getting a CE mark approval in Europe. We never could even get approval for an investigational study in the U.S. So we just basically kind of ran out of money, and so ended up not being able to continue with this particular device. I thought it was very clever. It was a mechanical device rather than a hydraulic device, and so it had some things going for it. You could leave it deflated for extended periods of time, whereas for the inflatable device, that was a little more difficult, although I think they did change the valving somewhat, so you can leave it deflated for an extended period, but I think it's a rather complicated operation. This one, for example, they could turn it off every night and make sure that vascular supply was maintained and decrease the amount of time that pressure was applied to the urethra. So that was something we worked on for quite a while, and but have basically aborted on that one. Also developed a device for external compression of the penis. This is again done at GT Urological. It's a padded closure that prevents most leakage. It has a discrete size and shape, and then it was suggested to me by a urologist who was using different clamping devices. So she said, well, why can't you put a little pouch on the end of this? Like they have pouches for male incontinence, and put that on the end of this clamp. So just in case the guy coughs or strains or has a little leakage, when he does, he won't soil himself. I said, oh, it sounds like a good idea. So anyway, we call it the ActiCuff compression pouch. You squeeze the side and it opens. I don't know if any of you have had a coin purse that you squeeze the sides and it opens. I think there's even a name for it. I can't remember what it is. But you can squeeze it and it opens, and you can place it over the penis, and then release it, and it's comfortable, and it's enough to prevent most leakage. And if you do have a little couple drops sneak out before you can get to the bathroom, you can take it off and you don't soil your clothes and get it put on a new one. It's easy to use at a urinal, and it's can be reapplied quite easily. So, as I said before, the technology and technological and urological interface is a combination of business, urology, and technology, and it really takes all aspects of that to really make a successful business. And it's been an interesting journey. I'm back on the faculty, and my idea is to continue to work in repair and replacement of injured organs, primarily the lower urinary tract. And so we've done a variety of things since that time. If we look at an injury model of the lower urinary tract, and so we did some tissue characterization, some finite element modeling. So, we developed some ambulatory monitoring devices to determine when leakage would occur, and then continued to study the neurophysiology of the lower urinary tract. Some of the current research is associated with finite element modeling of the pelvis. We did a study of female athletes and found quite a number of young women had some leakage issues, and so which seemed totally counterintuitive to us. So we decided to do some finite element modeling and to try to simulate what happens to the pelvic organs when they jump and strain and do different things. So we developed some ambulatory measurement devices to measured acceleration, measured inclination, and measured pressure, and leakage. So we're continue to work on mechanical tissue properties characterization and trying to improve on our model. So this is kind of a cycle that you go through. Let's say we started in the female urinary incontinence, and let's study the biomechanical mechanism, and we do a computer model of it, can do some dynamic biomechanical response, and it tells us something about the nerve tissue injury model, and hopefully lends to a better understanding. Or we can look at the neurophysiological mechanism to develop a live model, an animal model, and again, do the nerve muscle functional status assessment and hopefully come up with better solutions for urinary control restoration in women. Here's some of the modeling work that we did, some finite element modeling, and this was just, we did a very simplified 3D model of the female pelvis and just tried to understand how pressure gets distributed. And this was in a case when somebody jumped off a 3-foot platform, and you can see the red areas, how the intensity of the pressure increased and where it was located. So we've also studied material properties of tissue, where we're able to get fresh cadaveric tissue of the different organs, and that then feeds into our pelvic modeling device so we can do some better simulation studies. So, for example, urine is incompressible, but it allows for a good up equation of state for bulk response. So it's inviscid, so it's a simple Newtonian viscous shear model. And then bones we just assume they were rigid. So this was where we did a 50 milliliter displacement, and you can see the results of the individual, the simulations of this individual pressure distribution. Here's just some continuations of that study, and just an interesting way we can model using finite element modeling methods and kind of simulate how pressures get distributed in the pelvis of a particular individual. Our intention is to eventually make it patient specific, and so you can literally do a CAT scan or an MRI of the pelvis of that individual, and we can do our modeling work once we can get a better understanding of some of the tissue properties, and we can probably try to simulate what's happening in that individual. And then if that individual has corrective surgery or some other device implanted, we can re-perform that analysis and see if we've succeeded. Here's a comparison where we did a study of 16 different cases and just tried to see how the pressure was distributed. And this is a effect of stiffness of the pelvic muscles. This is another variable, of course. When you're active, your muscles aren't just passively sitting there; they're also responding. So we were trying to do some simulations of how stiff the muscles become, and obviously they change properties too during the course of one of these simulations. So In conclusion, we figured out the biomechanics of urinary incontinence of these female athletes during physical activities, and we know that jumping height has a large effect on the opening of the urethra, and so that may be in part what some of these athletes are experiencing. So we continue to evaluate the effect of the urine fluid flow and looking to improve the model as we gain a better understanding of the muscles and the fascia and ligaments and how they interact. And then try to account for the differences that may occur from one individual to another. So from this, like I said, I spent my first 10 years on the medical school faculty, and I spent about 25 years out in the private sector, and a variety of different companies have gotten involved along the way, and some of which no longer exist in that particular format. But the devices are still there. And this is an example of a deformation study. See, I don't know if I have. No, I don't have that loaded. Okay. Yeah, this is what we found in the female athlete study. I had one of my students who actually was a Gopher athlete, and so she knew all the trainers and coaches, and she got all her girlfriends and athlete colleagues to participate in a survey. I think she sent out about 240 or 50 surveys and got back about 170. So we got a very good response, and we can see that when we monitored when the leakage occurred, it was typically associated with vigorous activity, and not so much during daily activity, but primarily during vigorous activity. So 1 year we did the athletes, and then the next year we did an age-matched control, and we found quite a difference. The athletes had a considerably higher prevalence of urinary leakage issues than did the non-athlete population, which we found kind of interesting, which was totally counterintuitive in my opinion. These are some of the tissue testing methods that we developed in order to develop the database. It's basically a linear tester that stretches the tissue and up to a certain point, and allows us to improve our models for these simulation studies. So here you can see some of the tissue material properties. We did more than 100 cadavers and tissue specimens over the course of a number of years, and developed a more realistic geometric model based on patient CT images. And so this is just an example of a stress strain curve that we measured. Here's some of the methods that are used. The real geometric model of the female pelvis is developed from their specific CT images, and every one is slightly different, and so that's basically how the procedure is done. So our intention is to continue this work and develop a better computer model for doing these simulation studies, and do a better job of determining pressure and distension, other parameters involved. That would likely produce irreversible injury. In other words, how much tension or how much pressure can tissue stand and recover versus being unable to recover. So we developed an ambulatory device for recording a urologic response that athletes could wear partly when they're working out, and then they could also wear later after they were, let's say, less active, less vigorously active. And so we found, like I said, over 50% of our athlete population had some issues with urinary control. So we wanted to find out when does it occur, how much, and why does it affect some and not others. So this is kind of the way we did it. We used a triaxial accelerometer, a biaxial inclinometer, and a urine leakage detector. We spent quite a number of years working on some kind of a method to quantitate the amount of leakage. We never really were totally successful. We could tell when leakage occurred with using a pad test with some electrodes embedded in it, but we really never developed a way to measure what the volume was of that leakage. So we would do that recording, and the data could be transmitted wirelessly to a receiver and downloaded and processed. And this is, like I said, the subject will wear it for about 3 to 5 sessions for about 3 hours each session, and they will perform vigorous activity like they typically engage in while working out. We tried to locate the sensor, the accelerometer and clinometer, kind of at the base of their spine, which we thought was probably closest to the pelvis in terms of behaving like the pelvis, because that's really what we wanted to know, was how does the pelvis move. And so, so that was basically the procedure. And you can see, here's an example showing some high G values, up to 7 gravity, 7G, experienced during a simple physical activity involving jumps from various heights. So you can see there's a lot of pressure, force being exerted in the pelvis during these activities. So this hopefully will allow us to determine if incontinence occurs during physical activities or as a result of fatigue caused by these activities. I mean, it could be that after they're done working out, they're just tired, their muscles are fatigued and worn out, and maybe that's when leakage occurs. So in part, we hope this will help us understand the pathophysiology of urinary incontinence in a clinical population as opposed to our, let's say, our healthy adult population. Also can be used to develop training protocols that could, there could be certain other exercises that are performed that would prevent the occurrence of leakage. The ultimate goal is, I call it total bladder reflex replacement. The total bladder's primary function is storage of urine, and with intermittent expulsion based on, I call it a volume sensor, based on what the volume is. And so you deflate the incontinence device, the cuff that I show there at the bulbous urethra, and activate the detrusor muscle stimulators. And when we developed that device, we would apply the signal in a way that mimicked the natural contractile sequence of the bladder, so that we would make sure we got very efficacious and complete emptying of the bladder. And so, so that was kind of, it's really been probably more of a dream than a reality, because it's to put all 3 together in one patient, that might be a challenge, but doesn't mean it can't be done. So here's, we plan on continuing to the extent we can. It's always difficult to get funding, as you can imagine, but we're working on urge incontinence and detrusor overactivity, always looking at different ways to do bladder volume sensing. There are devices now that are used for bladder volume sensing using ultrasound applied to the abdomen, and they were able to get a fairly reasonable measure of what the bladder contents is. Doesn't provide a sensory feedback, but it does provide a volume measurement. A lot of future research opportunities in sexual disorders in male and female, and it's always, I always feel very happy that I was able to contribute in a small way to male sexual disorders with the penile prosthesis and the Rigiscan and the snap gauge and vacuum erection devices and things like that. But I've been starting to talk to some research people about female sexual disorders as well, and so hope to be able to continue that work. There's also an opportunity in gastrointestinal disease, gastroesophageal reflux, fecal incontinence. Those are some opportunities that are currently available, and I know there's a fair amount of work being done in those as well. So in summary, there's you need product differentiation to have an opportunity in the marketplace. I mean, it's pivotal. You need to have some way to differentiate and hopefully have some intellectual property to protect it. You want a defensible legal position. So you need evidence of value creation. You can create value either by improving outcomes or by decreasing costs. So either way is a way to create value for, and that's obviously that's very useful for fundraising purposes too. If you can show somebody that you're actually making people's lives better, and it's being reimbursed, the medical community values it as well, and you've got strong product champions to go out and talk about it, who are very honest and diligent and forthright, and then management skill, commitment, and discipline. It's always part of it. Is you have to be able to execute your plan too. You make a plan, but then you also have to be able to execute it. And that's it. Thanks for coming.